So, hello everybody. Next up we have Mathias. He will talk about the Android security model and layers and what's going wrong with them from time to time, and especially what can be done about it. Give him a warm round of applause and his stage.
Okay, good morning everybody. Thank you very much for the warm introduction. It's my pleasure to be here. It's a pleasure to talk about advanced Android archaeology. We've spent quite a bit of time doing research on Android and explored a couple of nice, interesting security issues that you may have noticed when you're working on Android. Quick show of hands, who's using Android? I'd say about 80% iPhone. A few others. iPhone users, where are you guys from? Netherlands? Serbia, a few? The Serbian ones? Quick show of hands. Usually it's a very nice split between Android and iPhones. In Switzerland it's about 50-50. In most other countries it's about 80-20. It kind of displays the socioeconomic wealth of different countries. The more wealth there is, the more iPhone users generally there are. It's an interesting study as well. But we're not here to talk about economics. We're talking about Android and kind of Android complexity. And on Android, you've got the full range of super cheap phones to super expensive flagship phones. And we're going to look a bit into the security issues across all the different layers of the stack. And Android complexity is kind of beyond all imagination. It's incredibly complex. It's an extremely scattered ecosystem across a large variety of diverse systems. There's more than 3 billion users across 190 countries. Massive, right? 3/4 of the market share worldwide are Android devices. There's 2.6 million apps in the Google Play Store and 1.5 billion devices sold each year. It is a crazy amount of complexity. And a couple of years ago, about 3 years ago, we started looking into the Android ecosystem and wanted to figure out what the kind of security primitives are. And to figure out what the security primitives are, you first have to get an overview of the system. And we tried to download a couple of firmware images, a couple of apps. We started some scripts. A couple of hours later, we accidentally downloaded several terabytes of system images and about 11 terabytes of apps. That ended up on our hard drive, which kind of formed the basis of a lot of the exploration that I'm going to talk to you about today. And we started shuffling through these systems images, trying to understand what the different aspects are. And I don't know how familiar you are with the Android ecosystem, so I'm going to start with a bit of an overview, right? The Android architecture, these are these little kind of thingies here that have a very glaring big screen, and they kind of have two worlds that are displaying to you. On one end, there's the normal world where you're running your apps like Google Pay, Netflix, WhatsApp, Signal, Duolingo if you want to learn a couple of quick sentences in Serbian before you come to the country, and a bunch of other things, right? So this is all running in the normal world, but in addition to the normal world, because the normal world sucks and is full of vulnerabilities, you also have the secure world on the other end. And in the secure world, you're trying to run all your secure applications. And you may not recognize the logos here, but there's a bunch of applications running on this secure world that is separated from the normal world, that stores things like your fingerprints, your keys for encryption, general other authentication keys, tokens, passwords, everything else. So these applications are generally working with highly privileged data and should be protected from the normal world. And there's some kind of interaction between the two. You're kind of often using the trusted world and interacting with it without really noticing, right, whenever you enter a password or whatnot. And if you look at the Android attacker model, the assumption is that, well, the normal world is compromised. There's going to be malicious apps in here that the attacker has control of, and the system needs to protect against fully malicious apps that are trying to exploit their privileges. There can also be bugs in applications, such as in WhatsApp, for example, through kind of native libraries that are unpatched or potentially vulnerable. And there can also be bugs in the trusted applications. And as we'll also see as one of the explorations that we did, we found bugs in this communication layer across the two systems as they are interacting with each other. So there's a lot of complexity here in this space, and let's try to figure out one step after the next where the different potential issues are. And we're going to start easy. You know, it's an early day. We're going to start easy, and we look into cheesing Android trusted applications. And it kind of means without any kind of effort, we want to get ODays on the Android trust zone protected area, right? We want to start the day easy, right? So not too much effort. And if you look at trusted applications, one of the big issues is how do you get the trusted applications actually into this trusted environment, and how can you make sure that they run safely? Well, trusted applications usually work in a way that they are signed binary blobs that are then loaded into the trusted role and trusted execution environment, where the operating system checks the signature. If the signature checks out, yes, you can run it, right? Now, one of the issues is that these applications are just as buggy as any other application. And if you have a bug in this trusted application, you can still load it and exploit the underlying vulnerability. Now, when we started looking at this ecosystem, we immediately wondered about replay attacks or rollback attacks. Let's say you have the old version of the app that has a bug, and the new version that does not have a bug. And instead of loading the new version without the bug, the attacker can still load the old version with the bug and thereby exploit an NDA vulnerability. Now, how do you solve this? What do you think? How do you solve this? What's the general approach to solving this?
Like version counters, and you don't allow rollbacks of application like it does in Android for updates?
Yeah, so you start issuing rollback counters or versions, and only the latest version can be loaded. Amazing idea. Simple concept, works really, really well. Let's see if this is actually being done. Right, so the concept works a bit like this. Instead of just having the different signatures, you add a little version on it. The trusted side keeps track of the latest top version and ensures that you cannot load any older version, and would then prohibit the loading of this version. Very good. So what we did is, based on the couple of terabytes of systems images we had, we scraped all the trusted applications and started analyzing how prevalent the use of these version counters actually are, and if people actually update the version counters whenever they patch vulnerabilities. So we targeted 5 different OEMs that cover about 65% of the market share. We looked at all the firmware updates over the last 4 years, grouped phones by ODM, and then analyzed the different firmware images, extracted the trusted applications, which gave us around 35,000 trusted applications, around 300 unique across 40 trusted execution environment implementations. We looked at rollback counters, and then also scanned public vulnerability announcements to see when vulnerabilities were fixed in these systems and if they actually increased rollback counters. And then we analyzed the actual details. And we discovered that companies are really shitty at updating rollback counters, as it turns out. They often forget, they silently patch, they patch only some applications and not others. And they're generally, it's a bit of a neglected kind of area. There's much more details in the paper. I'm just going to give you some of the highlights. That the TA rollback prevention is very, very incomplete with very questionable TA vulnerability practices. So different teams will be patching vulnerabilities without updating the rollback count, without actually doing a disclosure, without any notice. And the underlying assumption is same as with if I roll out the next update, this is going to be fine. But they don't consider that an attacker can diff. And it's still signed, right, the old applications. If you don't update the rollback count, we can just roll back. So this is a pleasure trove for end-day vulnerabilities that are readily exploitable. Also, looking at the one big vendor where the different phone lines start with an S or an A, what they often do, they fix the vulnerabilities in the phone with the S and forget to fix the vulnerability for the phones with the A. Now the thing is, the certificate is the same. So you can just cross-load across the two different phone lines and thereby exploit end-day vulnerabilities on both of the different targets. Full data set is available. You can check out the paper if you want more information. But that was a nice way to get us started in the Android ecosystem, looking a bit at how to exploit end-day vulnerabilities. Now let's try to ramp up the technical aspects a bit and we're going to stay on the trusted execution environment and continue looking at trusted application, because they have the richest set of information that can be useful for us. So we're going to look at trusted applications, but now we're trying to up the game a bit and we'll try to exploit it. Now, if you look at the two systems that are interfacing with each other, there's the normal world that is calling into the trusted applications, and to actually call into functionality of trusted applications, you need to go to the secure monitor and down to the trusted OS and then down to the trusted app. And we've been wondering, are there kind of bugs and vulnerabilities in this trusted app? And we observed that there's an internal API that's shared. Some of you may have heard of it, and it's called the Global Platform API. It's a kind of a communication protocol, how you can do something like an RPC call into a trusted application. A good thing is this gives us a standardized API that we can analyze. Remember, these are binary blobs that we have, these trusted applications, and now we want to start fuzzing them on a phone. The benefit is, by just observing this communication, we can extract the buffers, we can extract the API that these applications accept, and then kind of develop a fuzzer pipeline with fuzz drivers that then allow us to exploit that. So we did such a fuzzing pipeline where we analyze all the client application in the normal world. We extracted the interfaces, observed the communication on real phones, developed a fuzzer, recorded initial seeds, and then did some fuzzing on top of that and found a couple of bugs. It was a very nice system, also open source. You can play with it if you want. But as part of this process and when we started reporting some of the O-days we found as part of this system, we kind of noticed how fucked up the Global Platform API actually is. Now we have to think of, who knows Global Platform? Quick show of hands. Nobody, cool. So let me dive in a bit and explain you this protocol. You can think of this as you're going from the untrusted world and you're doing an RPC call into the trusted world. And you've got this RPC endpoint that handles arguments from the untrusted side that are controlled by the attacker. So let's have a look at a simple example here as you are calling into a trusted application. And this is like an RPC endpoint that we are looking here. And you see that the function prototype is the standardized function prototype for trusted applications. And let's look at this for a bit, right? And walk through the different parameters. And bear with me for a bit to handle the different complexities. So this is the session context. It stores the session state to have some kind of state through continuous calls into the trusted application as you're walking through it. This is controlled by our runtime system. This is somewhat fine, right? We assume that this is not tampered with. The other arguments are controlled by the attacker, right? But you're in the context of the trusted application. The other arguments are controlled by the attacker, including something like a command ID, okay? Fair game. There's like the system call or the feature that the attacker wants to execute. And now comes the parameter types, which determines the types of parameters. And I should have underlined this like 5 times. If the type is a memref, then the runtime system validates the reference that is being passed in the other parameters and ensures that the pages are mapped, that you have access to it, and everything is fine. And then you have the 4 different parameters. This is a struct, so let's unwind this struct for a bit. And now if you're in security, your alarm bells should start ringing. It's a union between a struct that's a buffer and size and a struct that's 2 integers. And remember, the attacker controls if this is being interpreted as the former or the latter. Okay? And the security check is only done if the parameter type is a memref. Otherwise, there's no security check from the runtime system. This is perfectly fine. Nothing is going to go wrong here. But, you know, we're going to be safe, right? Because you see here there's a check, right? You check if the parameter types are actually what I expect, and if the parameter types in your function, that's a recommended behavior, right? You're checking the parameter types. And if the parameters are not what you expect, you just return T error bad parameters, and everything is good, right? So we're safe. Now, and then you handle the parameters. Now, thanks to the specification that was done by a very clever security engineer, this check is optional. It's recommended, but it's optional. What could possibly go wrong, right? And then you access the different parameters at the bottom. Now, if the attacker classifies this as an input parameter, right? The values are not checked, which means the application, if you don't check and don't return after a bad parameter check, you're just accessing random memory, which turns into immediate, obvious arbitrary reads and arbitrary writes in the address space of the trusted application. Right, but the programmers were obviously aware that this is an untrusted attack surface, right, where the parameters are controlled by the attacker. Nothing like this would ever happen. So we wanted to verify this. We wrote a quick Ghidra plugin that does binary analysis on the flow of the different parameters, checks if the T bad parameter check is actually happening, and flags if something bad is not checked. And then we get a list of all trusted applications and entry points that would have this missing check. So let's walk through this for a bit in an example, right? We've got the first example here. We walk through, these are the parameters that are being passed and controlled by the attacker, passed to the vulnerable function, into the vulnerable function. There's no check. We're loading the two values. So this could be a memref or an input parameter. No check is happening, but this is not interesting, right? These values are just read. So we would analyze this, look at this in Ghidra, and say, yeah, this is not going to be an interesting one. This is a false positive. The check is missing, but no harm is being done. Now let's look at a different example, and this is implemented based on a bug that we found, a bit paraphrased and summarized. So again, the parameters are passed into the vulnerable function. They're being read. Parameter types are not checked, but this is actually interesting, right? So this turns, as you see here, the two highlighted points where the buffer is being read. This kind of means that the attacker can pass this as a type value input. The runtime system does not validate the buffer address, and the trusted application accesses it, and you've got an arbitrary write in your trusted application. We scanned the ecosystem of all the apps that we had. About 7,000 trusted applications were global platform compliant for 130 unique trusted applications. 850 were vulnerable, and 33 unique vulnerable trusted applications. 9 of them were publicly known based on earlier disclosures. We found that across the ecosystem, 10 were silently patched. Now think back, right? Silently patched means the rollback counter is not incremented. So this is something that you can still exploit. And 14 O-days that we reported got a little bit of bug bounty money and actually turned this into a nice system. Now, we're academics, right? So we are interested in actually fixing the underlying issues and vulnerabilities, not just pointing at vendors and saying you're doing crap security work, but we're actually interested in pushing this further. So we worked with the global platform API consortium, and we changed this, or we suggested a change from a fail open to a fail closed, which means that the type check becomes mandatory. When you're registering your functions, your trusted application functions into the ecosystem, you're giving that these are the parameter types I actually expect. So there's a fail-safe abort without the proper check. We sent a proposal to the global platform. It's a draft API for the draft for the API update, which is in progress. And global platform is actually changing their API and making these checks explicit. And the consortium was very happy to talk to us until they read the name Global Confusion of our paper that we published. But it still turns out that they accepted our suggestion, and this is going to make Android phones safer going forward. Very nice, so very good, right? We've got the trusted environment safe, we've got everything secured, everything is gonna work out well, right? No more bugs in trusted applications. Famous last words, exactly. So we started looking a bit into this communication channel here, right? Because if you know the ARM ecosystem, to call into the trust zone, trusted execution environment, you have to go to the secure monitor, which is, think of this as ring -2 on x86. And obviously this has to be very safely implemented, right? Very carefully vetted. There's not gonna be any security vulnerabilities in there. It's gonna be perfectly fine. There's gonna be no issues there, right? So when you're calling into the trusted application or in the trusted OS, you're calling, so an SMC call into the secure monitor that then funnels back up into the trust side, and doing this world switch between the two worlds, between the normal world and the secure world. And we kind of looked if, we wanted to figure out if there's bugs in there. Now, this is a very challenging environment to actually analyze because it's closed source. Vendors obviously don't release source code for all of these details or documentation. And this kind of interacts with a lot of different system components that are very, very hard to analyze. So what we face is this major challenge of limited introspection. We cannot really run this stuff, right? This is very hard to peek in. We initially thought about running this on the phone itself, but then you just have random crashes, and it's very hard to kind of debug and figure out if it's a real or good bug. So we tried to look into a rehosting approach of taking the secure monitor, the binary blob, and running it in a like beefed up QEMU that we kind of cherry rig into getting the secure monitor to run. But the issue is the secure monitor is interacting both with the trusted OS, the rich OS, the bootloader, different kind of peripherals and whatnot. Is going to be very, very difficult to look at because there's so many additional complex dependencies into other software running on the system, but also the different peripherals, because it has raw hardware access, right? And you don't want to implement this for every single little phone that we're looking at. So the two main challenges that we face are these software dependencies and the different peripherals we're looking at. And the operating system is very, very complex, right? In the SMC, you give a 64-bit number to the dispatcher, which is a function ID. And we now have to figure out what all of these different systems are. Think of it as like you have no idea. The only thing you can control is the system call number. You're calling into the operating system and have to figure out what kind of vulnerabilities are in there. It's kind of a challenging situation. There's very different set of function calls that you can do, like architectural calls, CPU service calls, different kind of OEM vendor-specific calls and whatnot. That's very, very hard to figure out. And none of this is documented, right? So we can randomly shoot in the dark, but it's kind of it's without good feedback, we're not going to get any reasonable, useful results out of that. So what we did is we designed Elixir, which is like a magic potion to analyze this underlying system. And our core idea was that we snapshot the secure monitor. We kind of fix this into a somewhat booted state, let it interact with the peripherals, and let the fuzzer figure out the peripheral interactions, and then develop a very nice harness that allows us to explore these targets. Now, a contribution that the hacker community will appreciate, but not the academic community, we kind of had a developer in the loop boot up process, where the developer or the analyst takes a secure monitor, starts running it. Whenever it crashes, we fix it. There's an MMIO space here. We hard code. This is a link here. We kind of link this MMIO space, this MMIO range to fuzzer input and whatnot. And we kind of step by step, iteratively refine the configuration for the system so that we get into a snapshot of a booted secure monitor inside our QEMU. This takes about 2-3 hours of figuring out the different I/O ranges for the targets, and you're just like encoding the configuration to make sure this boots up and that we can snapshot it later on. The second contribution is reflected peripheral modeling. We initially considered hiring master students to implement all the different peripherals, and which is not a great, very useful idea. So we instead let the fuzzer figure this out directly and just feed fuzz input to all the different MMIO ranges that we have mapped from before. And the fuzzer kind of coverage driven tries to figure out all the different ways how we can drive complex interactions to maximize the underlying coverage. Then we look at the rich OS, the source code from the rich OS, which is the open source component. We extract the different interactions with the secure monitor, recover the interface, create the harness, and then just start fuzzing. We looked at 7 targets from 6 different vendors, 4 open source, 3 closed source, triggered 64 bugs, 17 O-days and 5 targets. And we got a nice set of a bunch of CVEs and bug bounty money, including, again, a shout out to the nice company with the 2 different lines of phones with the S and the A. We had 5 distinct bugs that they reported, but due to internal pressure, where the teams get punished for each additional bug that they report, they only gave us 1 CVE for 5 distinct bugs. You know, every company has their own policies, and there's interesting trade-offs there. Very cool. Quick slide that our fuzzer explores more code than others, but you can read about that in the paper. So to summarize for Elixir, the goal was to fuzz these custom off-the-shelf secure monitors. We developed this rehosting framework that makes it possible for analysts to kind of dive deep into these underlying systems and develop this automated fuzzing pipeline to find O-days. It's open source, you can go play with it, rehost your favorite secure monitor, find O-days and get rich, and report the bugs and at least acknowledge the work that we did for the open sourcing. So far so good, right? Now we've covered trusted applications, we've covered the secure monitor, now we're good, right? Android is safe and there's no more to worry about. So let's maybe have a very short look and spend a couple of minutes in the normal world, right? The normal world is already fucked up, but we're trying to understand a bit more on how these interactions actually work. Who has played with memory allocators? And very nice, a bunch of people, right? And the Android security team spent a lot of effort on securing allocators. Who knows Scudo, the Scudo allocator? 1, 2? Cool. 3 people know the Scudo allocator. It's a hardened memory allocator, right? So a hardened memory allocator that makes heap exploitation as hard as possible. It's a user-space memory allocator, so it's a drop-in replacement to your regular ptmalloc or whatever allocator you have. And it's designed to prevent exploitation of heap-based memory corruption vulnerabilities. So Android actually deployed with Android 11 Scudo using the security-first approach, making sure that the heap-based exploitation is as hard as possible. Now, how does exploiting the allocator actually work, right? So the underlying idea is you've got your application that does malloc and free, you go through the allocator manages the heap memory, kind of shuffles blocks around and gives you access to the different bits and pieces. Now we assume that the application contains heap vulnerabilities such as overflow, use after free, double free, and whatnot, which are all nice vulnerabilities, but they are kind of a pain to exploit. So you usually want to fudge with the data structures of the allocator to turn this into arbitrary reads and arbitrary writes, so they have a very powerful primitive for later exploitation. So this is like an approach to make a heap-based buffer overflow into an arbitrary write, which gives you much more control over the application and makes exploitation much easier. So you corrupt the inline metadata, which is just adjacent to the object, and then as the allocator goes through, you can turn this into an arbitrary read and arbitrary write. And for the connoisseurs of good literature, there's a bunch of very nice articles in FRAC from the late 90s, early 2000s on different kind of heap-based exploitation techniques, how to actually fudge with these data structures that were kind of an inspiration for all of the work that we did. Now, Scudo is hardened against such attacks, and the key goal is that such attacks are no longer possible, right? And Scudo went through a lot of additional effort to ensure that you can no longer just overwrite the metadata without it being detected. So let's have a look what sudo actually does. First off, sudo does randomization. Right? Sudo randomizes the address of allocation. So between two runs, two executions of the program, there's going to be a randomization seed, and then you shuffle the allocations throughout. And each time you execute, there's going to be a new seed, and the allocation sequence will be shuffled, which is going to make heap grooming much harder because the objects are no longer placed in the same order in the same location. Very good, right? So this is going to make exploitation much harder and the application safer. sudo also protects inline heap metadata. Right? So all the different chunk headers, they are being signed. And whenever the data is being used, sudo actually verifies the signature before parsing the metadata. So if you overflow your metadata, you're going to invalidate the signature, sudo crashes and aborts the process. Now, what's the issue?
If you know how a signature is, you could still craft a valid signature and still overflow it.
If what?
If you know how the signature is done, yeah.
If you know how the signature is done,
you can make a valid signature at the end of the buffer.
If you know the randomization seed, right?
Yeah, true.
How does it protect against that?
Well, you would need an arbitrary. The question is, how does it protect against the randomization seed being leaked? Yeah. You would need an arbitrary read to read the randomization seed. Therefore, the assumption is this is already okay, right? If you already have an arbitrary read, you don't need to turn the heap-based buffer overflow into an arbitrary read. Right? It's like an apple and egg, right? A chicken and egg problem. So yeah, but the basic assumption is that if you know the randomization seed, you would be able to bypass the defenses, right?
But wouldn't you still could like overwrite the victim chunk and modify at least this chunk? I mean, the first chunk is like invalid because you don't have the signature, yep. But you still can overwrite the victim chunk.
You can overwrite the victim chunk, but it's not going to be used because before the data is being used, the signature check is being done. So this is done very, very safely, right? The only way you can get around sudo-based allocation is by actually leaking the randomization secret. How do you leak that? Who knows Android? What does Android do? How does Android ensure performance? Right?
Is it like the cache or something?
Not the cache, but like so. This system, the sudo-based system, is very, very safe. The only way how you can attack this is by knowing the randomization numbers, and if you know the randomization secrets, you can actually bypass all these protections. Now, let me give you a 2-minute introduction into how Android handles application. Android has the so-called zygote process. Because it takes like 5 seconds to load the runtime execution environment, so they preload and kind of have a fork server after everything is preloaded. Right? So they preload all the libraries of the runtime environment for all the application and then just fork. Now, let's assume we've got the zygote process here, which is the initial root of the system, and then you fork whenever you start a new application. The evil app or the victim app. Now what happens if you fork? Are you going to reinitialize your random numbers? Are you going to reinitialize your random seeds? No, right? The ASLR layout is going to be exactly the same across all the process. The randomization seed for sudo is going to be the same across all your processes. The signing key is going to be the same across all your processes. Now, as it turns out, by deploying this super secure allocator, that in any benign case, when you exec VE a new application, would have made execution much safer. On Android, it's just destroying security because you can leak the key across applications. And as an additional tidbit, also privileged system services are also forked from the zygote process.
Sad.
So this is a very sad state of affairs, and essentially ASLR and sudo secrets are shared across privileged, unprivileged apps by just forking the different systems. So as soon as the attacker has access to one application, they can read out these secrets and turn this into an exploit. We checked if this is feasible. and attacked the system server, which is a highly privileged process, hosting a bunch of different system services, and then exploited this over binder, and all happiness ensued for us and unhappiness for the Google security folks, because this is fundamentally insecure. The only way you can mitigate this is if you exec-ve a new Android runtime environment whenever you start an app. And guess what? This is exactly what Graphene does, but not stock Android, because on many of the systems you have very little memory, and this would increase the memory pressure. Very nice. So this was then the inspiration to continue a bit more looking into native Android system services. Because what we saw here is that exploitation happened across the binder IPC. So we figured we'll explore these native Android system services a bit more, as a lot of privileged functionality is exposed on Android through these system services. Before, in previous years, one of the prime exploitation targets for unprivileged applications was the Linux kernel and the binder IPC interface. But all of this has been rewritten in Rust. It's much safer now, so we can no longer easily target and cheese the kernel. So instead, we're going to go for the privileged system applications that are running as root and are trying to attack those. So we explored this a bit and developed a deserialization guided interface extraction. It kind of does a binary analysis on the interface these binder services accept, and then we created a fuzzer that targets these different binder services, found O-days, got some bug bounty money, and Google fixed most of the underlying issues in the system services. So as an interesting exploitation target for you folks, the kernel is much safer now, protected against different kinds of exploitation on Android. System services are still an interesting attack surface, especially those that are pre-shipped by different vendors. Now, we also wanted to look a bit into how Android unsafely reuses shared libraries. If you've ever done Android application vibe coding, the general approach is you just dump all the different shared libraries that you find for random functionality in your folder, you package everything up, and then you go for it. So we had an amazing research plan to assess the Android app ecosystem. It's a 5-step plan. We download some APKs, we build some binary similarity thing. We detect custom patches in Android native libraries. There must be vulnerable, right? Bad vendors, bad. We're going to report you. We're going to get rich, publish, profit, many citations, and we're going to be rich. We never got past the first step, unfortunately. So let me explore and expand on this for a couple of seconds. First, to develop any kind of binary similarity thing, you need a large data set for ground truth validation, how well that actually works. So we scraped all the different markets, Playdrone, a bunch of others, and whatnot. We downloaded these 8.7 million APKs. A good 12% of them have native libraries, which resulted in 1 million unique libraries across the Android ecosystem. Now, we had an interesting discovery at that point in time. Lots of code is shared, right, across applications. So the top 50 binaries that we found account for 14.3% of all native libraries. The top 5,000 binaries account for almost 80% of all libraries. So there's a lot of reuse, and then there's a very long tail of a few individual libraries in this ecosystem. Now, how do we infer library names and versions to figure out if they are vulnerable? Did I hear machine learning and AI? Of course, right? This sounds amazing. Everybody in today's world has to do machine learning and AI to clear all the buzzwords. We therefore explored the different areas. There's a bunch of papers in machine learning and in AI, and they're all promising amazing precision, amazing recall. They've solved the problem for us. Everything is good. We're done. So we looked into the system and also at their evaluation. And remember, right, we have a very large data set, and this really depends on how many individual binaries they can actually distinguish effectively. And these are kind of the evaluation results of the top systems. So obviously, when we started such an exploration, we're going to do a very sophisticated analysis on the capabilities of the existing system, run some machine learning on it, and then explore, extrapolate. This is exactly what we did. And we actually saw, based on our sophisticated scientific analysis, that if we scale towards a pool size that we're interested in, the recall, the usability of these systems is going to drop to 0. Top quality, right? So machine learning works great for small data sets, but it just doesn't work for large data sets that we are interested in because there's not enough distinguishable features. So for a toy data set of 350 binaries, which is already bigger than what these systems explored, it took us 12 hours to train the different embeddings. If you look at our data set of 1 million libraries, this would take almost 40 years to analyze for a system, right? So this is clearly not feasible. So this is pretty much the pool size that AI systems play in. And the pool size we're looking at Android is about 10 Olympic pools, just to give you a visual image on the difference in amount of different libraries they would have to distinguish. But then we started wondering, right? So machine learning clearly doesn't work, but do we actually need machine learning? This may be counter the current bubble in research, but we wanted to know that what can we do without machine learning? So we looked at all the libraries, and this is the count of the same of libraries with the same hash, where we indicate and analyze the different steps, right? When we see individual drops, and these steps indicate that app developers just downloaded tarballs and dropped into it. So we started exploring where do these binaries actually come from, and we started scraping random resource sites, and we discovered that if you just look at Maven, like one of the common systems, just looking at Maven itself, we can immediately match and know the versions of 30% of all libraries. Adding a bit of heuristics for React Native, which is just a cursed ecosystem that should die and be removed and burned again and again, we get to 60%. We can talk at the bar about this. We get to 60%. So we can now instantly recognize 60% of all libraries, no need for AI. And it turns out you don't need a fancy AI if everyone just reuses the same 1,000 binaries, right? So you can just do a SHA mash and then do the matching. So we wanted to know the details of these systems and if there's any actual vulnerabilities, because the app developers should patch, right? And we wondered, do they patch? Whenever there's a vulnerability in a native library, are they actually going to patch, or are they just going to forget about it? What's your guess? No. So let's be very, very generous. Who remembers Droids on Roids? Droids on Roids? This was a severe vulnerability in WhatsApp that allowed remote code execution on WhatsApp about 6-7 years ago. It's a GIF library parser that had an easy bug in there that gave you remote code execution. This was patched in WhatsApp 6 years ago. It obviously should have been patched here too, very, very quickly. So we scanned the Android Play market. There's 45,000 Android apps still using this vulnerable library, still using this library, and the CVE is over 6-year-olds. And 78% of apps remain vulnerable. They're still reusing the vulnerable Droids on Roids library that has this remote code execution bug in there. Filtering the only apps in the Play Store, it's 60% of apps. So 3,000 apps in the Play Store still use this vulnerable library. But you're going to say, Matthias, you're just joking. You're an academic, right? You're just blowing out these numbers. Nobody is going to have these applications installed, right? These are going to be some application that a student kind of listed some time ago. So let's look at some of the applications, shall we? Top 3 applications that are still using this library. Screen recorder, video recorder, 100 million plus downloads. Very nice. 143 million downloads for the screen recorder. 242 million downloads for paint by number, pixel, whatever thingy. And update news for Samsung. 403 million downloads. Amazing, right? Now, little caveat, right? Exploiting these apps may be hard or even impossible. You still need a vector where you can man in the middle, trigger the vulnerable functionality, but just using these or having these vulnerable libraries in the code is horrible, right? And you should obviously patch, and especially if you have like a couple of 100 million downloads of the system. So this kind of concludes the whirlwind tour across the Android ecosystem that I wanted to give you. And if you don't really know the group or what we are doing is, like, I'm not doing this by myself, right? I'm working with a bunch of super talented students that deserve most of the recognition for this research work. And we do a bunch of software testing where we aim at finding as many bugs as we can. We look at mitigation, making exploitation as hard as possible, and breaking up complex systems into as small compartments as possible. We're at EPFL, the Swiss Federal Institute of Technology in Lausanne, doing research in all areas of software and system security. There's always position for PhD students, postdocs, or visiting researchers if you want to come by. These are just a bunch of people I had the pleasure to work with at EPFL, and I usually just join them on a ride on the lake 5 minutes from campus or somewhere in the snow, in addition to giving some of these fun presentations. So to summarize Android security in one image, I kind of showed this burning dumpster fire, and Android security remains an elusive target, right? What's good is the per app compartmentalization, the underlying ecosystem is fairly well designed. Sensitive data remains in a trusted world. It's also a good security design to separate. What we expected, a bunch of bugs in the hypervisor, right? There's going to be implementation bugs. That's fairly obvious. What's really not necessary, like the vulnerable communication APIs for the global confusion attack. The rollback is just a mess that needs to be cleaned up. And there's a whole bunch of other targets that you can look at in the Android ecosystem. I hope I inspired you to do some research on Android going forward. I'm happy to stay around for more questions afterwards. Thank you for your attention, and yeah. I'm not sure how much time we have for questions. That's why I stopped you. Sorry.
I know. No worries. We have some time.
So we have some time? Okay.
I was just curious about your the libraries you were looking at. I really love this talk, by the way. It's awesome. Did you also consider looking at similarity hashing things to find more common libraries in the applications?
Similarity hashing?
There's many. You have the classic is SSDeep, which is not that suitable for code, but there's a couple of more modern ones that are now being used to see malware families, etc. I'm wondering if you considered using those for these libraries?
We considered using them. That's like we wanted to use this before machine learning. The initial problem kind of remains figuring out a ground truth data set to evaluate these systems. And the different similarity hashings we tried did not scale to the millions of libraries we had. So it was just, they were too slow, same as machine learning. And if you look at, we did a couple more tricks that are still under wraps, where we get the precision up to around 80-ish%, but just adding some more data sources. So our assumption is that just adding more data sources and doing exact hash matches is much more feasible than building a sophisticated technique. Question is if this is publishable or not, but it's got to be much better precision.
I have a tool that you might find interesting.
Cool. Maybe we talk more about that afterwards. Thank you.
So, hi Matthias. Roughly, how much money did you make on bug bounties, and what are you doing with it?
Good question. Now, I have a very conflicted relationship with bug bounties because we always do responsible disclosure, and not all companies are playing fair with researchers. I would say 100, 150K over the last couple of years. We're using it mostly for pizza money, retreats and stuff like that. Yeah.
Okay, any more questions?
thanks for a super awesome talk, and like also open sourcing your software and also making Android world more secure. I wonder, first of all, for the global protection API, is it only ARM specific one, or it's a general standard for also other processor types? That's the first question.
What do you mean by other processor types?
Like there are also like x64 that runs Android, and also there is MIP processors that run Android.
Oof. I'm not sure they matter, to be honest.
Okay.
There are so few x86 and other systems. First, like to answer your question, I have no idea. I think they're somewhere very far down on the tail. I don't think anything apart from ARM matters. Now, let me give you a little bit more information on the Global Platform API. Global Platform was one of several competing standards. Now everybody seems to be converging towards Global Platforms. This is becoming the standard for all the different systems.
So they were like a competition, and then ARM won.
Yeah. And across all the different vendors as well, they're all switching. Before, every vendor had their own communication. Now everybody's switching to Global Platform.
And I also wonder for the Android apps. I mean, you have several protection measures in hardware and in software, but you usually need to compile those applications with those flags. So what is the status quo on this? Because I also see it in the real world next to Android, like on real computers.
What are stack cookies, right? Why do
like
we need ASLR?
who needs that?
Who needs
and
that?
so what was your like overview about that?
We didn't run the exact statistics, so everything I'm telling you I'm pulling out of my ass. But we've seen several instances where these things are missing. There have been other papers that highlighted, hey, they're not necessarily compiled with security.
Thank you very much.
But that's Android ecosystem is kind of screwed up. It's also really hard. Right? You would have to deploy safe versions of all the different libraries. And Google would have to force the individual app developers to update their underlying apps, which they can nudge. So we are working with Google on nudges and reporting these numbers on all the potential vulnerable apps. So they're likely going to send emails, but then if a developer is not interested in updating their app, then there's very little we can do.
Delist that.
Yeah, delist the app, that's one option. Cool, thank you.
So, let's thank Mathias again for this eye-opening talk and give him a round of applause.
Thank you, folks.